Alright, hello. So today I'm gonna be giving you a quick demo about how my code works. So my project was about implementing one congestion control algorithm, and I chose this algorithm, which is called Copa. This was published in 2018. And well, this algorithm is a delay-based algorithm, congestion control algorithm. That means that it doesn't rely on packet losses to measure the congestion level in a network. Instead, it uses the round trip time to perform the control actions. It keeps track of the round trip times and how they change, how they're changing to perform the control action. Okay, so I implemented this algorithm in a Linux kernel module. Here you can see my implementation. This is my implementation. Okay, in a Linux kernel module, and I'm gonna use the NS2 network simulator to test this implementation. Okay. And I'm going to perform 3 experiments that the authors also performed in their paper, and I'm going to walk you through each one of them. Okay, so the first experiment that we're going to see is the dynamic experiment. Okay, so let's take a look at the script in NS2. So NS2 comes with its own scripting language that allows us to set up different network configurations and run simulations. So in this first experiment, we have 20 flows. We're going to have 20 sending hosts and 1 receiving host. The 10 sending hosts are going to be connected to a router, and then the router is connected to the receiving host. Each one of the links in the network is going to have the same bandwidth. It's going to be 100 megabits per second and 10 milliseconds of delay. And the 10 flows are going to be in the network are going to be entering and leaving at different points of time. They're going to start and stop at different points of time. So for example, the first flow is going to be active between 0 and 19 seconds. The second flow is going to be active just only between 1 and 18 seconds, and so on and so forth. The 10th flow, for example, is only going to be active between 9 and 10 seconds. Okay, so we can see that each one of the flows is going to be active during different amounts of time. So for example, the 10th flow only 1 second, the 9th flow only 2 seconds. On the other hand, the first flow during the whole 19 seconds that the simulation lasts. Okay, so we're going to be measuring the throughput at different points of time. And so basically we're going to be collecting the data of the 10 flows in different points of time, and then we're going to collect this data, and then we're going to process this data using this Python script. Okay, and we're going to be computing some statistics with these flows. Basically, we're going to be measuring the mean. We're going to have 10 flows, and we're going to be compute their mean, and also their standard deviation. Okay, and we're going to be doing that because we want to plot the range between one standard deviation from the mean. Okay, and we're also going to be computing a fairness index, which is called the Jane index. Okay, the Jane index is a measure of fairness in the network, and it ranges from 0 to 1. Value close to 0 means that the allocation is not fair, whereas a value close to 1 means that the allocation of flows is very good, is fair. Okay, and in order to show this in one plot, we're going to be plotting the gain indices in a cumulative distribution function. Okay, so that's basically what we're going to be doing in this for this first experiment. It's also worth noting that we are going to be running this experiment for not only for Copa, which is our implementation, but also for Cubic, Vegas, and Reno, which are other three congestion control algorithms. Each one of these, Cubic, Vegas, and Reno, are the implementations in the Linux kernel module that one can find in the Linux source code. Okay, so those are going to be our the methods, the algorithms which we're going to be comparing to. Okay, so without further ado, let's run the first experiment. Alright, so the first experiment is done. The data was generated and the plots were also generated, and let's take a look at the results. So let's, for example, see the throughput between Copa and Cubic and how they compare. So in this case, these are the throughputs that we got. The black line here means the ideal allocation. So remember that the throughput, the bandwidth of the links was 100 megabits per second. So that means that if there's only one flow in the network, then the throughput, the average throughput that we should observe, should be 100 megabits per second. If there are two flows active in the network, then the average throughput should be 100 over 2. If there are three, the average throughput should be 100 over 3, and so on and so forth. So for example, when we have 10 flows active, we should have 100 over 10 megabits per second, a throughput of 10 megabits per second. That's basically what the black line means. Here's, as I mentioned, we're plotting the range between one standard deviation away from the mean. As we can see, our implementation, which is Copa in blue, includes this ideal allocation most of the time, and also Cubic also includes that allocation most of the time. Okay, so this is one way of validating our implementation. So this is the results for Copa and Cubic. So we also have the results for between Copa and Reno, for example. Between Copa and Reno, these are the results. So the graph in blue is basically the same that we had for Copa and Cubic. We're not changing that. We're just changing the graphic, the plot of the other method. In this case, it's Reno. Here we can see that Reno, for example, doesn't do that well here. Most of the time, there are many points of time in which the graph of Reno doesn't include the ideal allocation of the flow. What about Copa and Vegas? Between Copa and Vegas, it's very similar to between Copa and Cubic. Vegas seems to have also a relatively good allocation. Yeah, these are the results for the throughputs. Now, what about the gain indices that we also computed? Let's see the results for the gain indices. So as I said, we're plotting these gain indices in a cumulative distribution function. Okay, so that means, so remember the gain index changes between 0 and 1. 0 is a good allocation, 0 is not a good allocation, and 1 is a good allocation. Since this is a cumulative distribution function, the vertical axis goes from 0 to 1. 1 includes all the flows, all the data points. 0.5 should include only the half of the data. and so on. Okay, so for example, one way of reading this plot is, okay, let's see, for 0.5, it means that 50% of the times we have an allocation above, for Copa, above 0.8. And the other 50% of the time, the allocation is below 0.8. So we can see that most of the data points we have a good allocation. All right, so these were the results for the first experiment. Now let's move on to the second one, which is fairness. Let's take a look at the NS2 script. In this case, we're gonna sort of similar to the previous one. The difference is that now we're gonna have 20 sending hosts. In the previous one we only had 10, now we have 20. The 20 hosts are connected to a router, and the router is connected to a receiving host. And the different thing here, as the 20 flows are coming from links which have a different amount of delay. So for example, the first link has a delay of only 50 milliseconds. The second link has a delay of 29.25 milliseconds, and so on. The delays are going to be spaced between 15 and 30 milliseconds. Okay. And we're going to be measuring fairness here. We're going to be measuring the average throughput. We're going to run the simulation for 100 seconds, and we're going to be measuring the average throughput at the end of each one of the flows. Okay. The difference with the fairness that we measured in the first experiment is that in the first experiment, the 10 flows were behaving in a different manner. Each one of the flows were active in different points during different points of time. In this case, all the flows, the 20 flows, are active during the whole time that the simulation lasts. That's the difference. The only thing that changes is that the link those flows are coming from have a different amount of delay. And we want to see how good the algorithm allocates those flows when they're coming from sources from links with a different amount of delay. So let's take a look at the script of the experiment. So again, we can see we're going to be performing the experiment for all Copa, Cubic, Vegas, and Reno, as we did in the previous case. Okay, let's run the experiment. Alright, let's see what we got. In this case, we only have one plot. So we have a plot which has 20 samples for each one of the algorithms. We have 20 hosts. We measure the average throughput for which one of the 20 flows. And what we're seeing is that all those data points are very close to the ideal location. Remember that the bandwidth, the bottleneck bandwidth, the bottleneck link has a bandwidth of 100 megabits per second, which means that if there are 20 flows that are going through that link, in an ideal case, the throughput for each one of the links should be 100 over 20, which is 5 milliseconds. So we can see here the black line lies exactly at 5 megabits per second. And we can see Copa, Cubic, and Reno are very fair. The allocations are very close to the ideal one. In this case, we can see that Vegas is not doing that well in this experiment. So the data points are from which one of the flows that were coming from links with a different amount of delay between 15 milliseconds and 300 milliseconds. Okay, so this was the second experiment. Now let's move on to the last experiment that we ran. Let's take a look at the next script. This experiment is a little bit easier. We only have two hosts, one sending host and one receiving host. The thing that we're changing here is that the link now has a now we are allowing the link to drop packets at random, and we're gonna change that rate at which they're dropping the packets with between 0% and 6%. We're gonna run the simulation for 60 seconds, and we're gonna measure the average throughput that the flows get. Okay. As we can see, every one of the flows, we're gonna be using again Copa, Cubic, Vegas, and Reno, and the rate is gonna be changing between 0% and 6%. Okay, so let's run the experiment. Alright, so the experiment is done, and let's take a look at the result. So this is the result. As we can see, the throughput decreases as the packet loss increase. That makes sense. And we see that Copa does a little bit better than the other three approaches. And for example, we can see that when the packet loss is 6%, the other three approaches have a throughput of a little bit above 0 megabits per second, whereas Copa has a throughput of a little bit above 2 megabits per second. And so yeah, these are results for this this experiment. All right. So yeah, I think so those were the experiments that we ran, and yeah, thanks for watching.